Okay, so for problem 66, it reads, astronauts use a centrifuge to simulate the acceleration of a rocket launch. The centrifuge takes 30 seconds to speed up from rest to its top speed of one rotation every 1.3 seconds. The astronaut is strapped into a seat 6 meters from the axis. A, what is the astronaut's tangential acceleration during the first 30 seconds? So for part A, we're going to need the circumference of the circle of the centrifuge that it's creating. Obviously, the tangential acceleration is what we're looking for. So I have the equation of what it is. It's the change in the velocity over the change in time, which is all accelerations, but we can use that for tangential acceleration. We also are going to need the rotational velocity. And then from all of those, we can find the acceleration, the tangential acceleration. So first, you just use your 2 pi r, which gets you your circumference of 38 meters. And the reason we need the 38 meters is so that we can convert the one rotation per second, or per one rotation 0.13 seconds into just 1 second, which can get us the 0.77 rotations per second. We multiply our 38 meters of our circumference by our 0.77 rotations, which will get us how many meters we travel in a second, which will give us our velocity, which will be 29.2 meters per second, but with significant digits, we now get 29 meters per second for our rotational velocity. So that's our change in velocity. And then we just need our change in time, which it gave to us as 30 seconds. So for our acceleration for tangential acceleration, we can take our 29 meters per second divided by our 30 seconds, and you'll get 0.99 or 966 meters per second squared, which with significant figures, we can get 0.97 meters per second squared as our tangential velocity. Part B asks, how many g's of acceleration does the astronaut experience when the device is rotating at top speed? Each 9.8 meters per second squared of acceleration is 1 g. So I have our list of equations we're going to use for part B. We're going to use F equals mv squared divided by r, which is the normal force equation for rotating objects. And we can substitute our rotational velocity squared times r for our velocity squared divided by r. And then we can also substitute our F for mass times acceleration. So we have our new formula, which is mass times acceleration, the acceleration for the rotation, and we get mass times acceleration equals mass multiplied by our rotational velocity squared multiplied by our radius. We can find our rotational velocity by doing 2 pi over time, because that is just figuring out over like how long does it take for us to get around 2 pi of the circle, which is the entire circle, back to our starting point. So that's 2 pi divided by our 1.3 seconds, because it takes us 1.3 seconds to make one rotation. And you get that our rotational velocity is 4.8 radians per second. So now we plug those numbers in. Our mass divides out on both sides, so we don't have to worry about mass of the object. So we just have our acceleration equals 4.8 radians per second squared multiplied by 6. And this gets us 140.16 meters per second squared. And then you're going to divide that by the 9.8 to get it to g's, which will be 14.3 g's.